Hi, welcome to Neutrinos from Home 2024. My name is Julian Heeck. I'm a particle theorist at the University of Virginia working on physics beyond the standard model. And I was asked to give a talk on why we care about sterile neutrinos. First off, why do particle theorists care about sterile neutrinos? I will argue that they nicely complete the standard model and increase the symmetry. And that is a good motivation to introduce them. But first off, we need to look at the standard model. These are all the elementary particles that we have observed over the last 100 years or so. Most of them should be familiar to you. You have the electron here, the photon over here. The newest addition is the Higgs boson that was discovered experimentally at the LHC about a decade ago. And this nicely completes the mathematical framework of the standard model. This is all that we needed for consistency. We've measured the masses, the charges, the spins of all these particles, and it's essentially precision physics in these measurements. The interactions of all of these particles are determined by quantum field theory, which is the consistent merger of quantum mechanics and special relativity. We describe it usually in terms of a Lagrange density that encompasses the kinetic energies of all particles. In this case here, these are the vector bosons, like the photon, the spin 1/2 particles, the fermions, so electron, neutrino, quarks, and the scalar, the Higgs boson, as well as their interactions, the Yukawa couplings between fermions and the Higgs, and Higgs self-interactions are encoded in this potential energy term over here. This is a very successful theory that describes almost everything we know about how particles interact at the most fundamental level. In a bit more mathematical terms, the standard model is a renormalizable quantum field theory in flat four-dimensional space-time. So the one thing we're omitting here is gravity, because it's notoriously difficult to quantize gravity. We're not going to attempt to incorporate that here. The ingredients for this quantum field theory are the gauge group, SU3, SU2 cross U1, each of which corresponds to an exchange force mediated by a spin 1 particle, gluons, W bosons, and the hypercharge boson, which will in the end become the photon. And all particles come in representations under this gauge group. On the scalar side of things, we only have one representation, the doublet with hypercharge 1/2. This will become the Higgs boson. This is the only scalar in the standard model. So with all bosons taken care of, the only thing left are fermions. They come in chiral form in this reducible representation. There's 3 exact copies of the same gauge representation. And we call all the particles that are charged under the SU3 quarks, and the ones that are not leptons. With this, you just need to write down all gauge and Lorentz singlets with mass dimension less or equal to 4, and you put them in the Lagrangian to get the standard model Lagrangian. Once you expand that out, you get all the interaction terms that you need to describe particle physics. When you do that, you realize quickly that you can't write down mass terms for the fermions because they are chiral, and because the gauge group representations are the way they are, you can't actually write down mass bilinears. Essentially, the SU2 cross U1 part of the gauge group forbids you from writing down the mass terms. That's bad news because we know the electron has mass and all the other charged particles as well. So something is off. And the thing that's off is exactly this SU2 cross U1 symmetry, which is not a good symmetry in nature. We understand now that it is spontaneously broken by the Higgs mechanism. So the Higgs has a potential that has a minimum not at 0, but rather somewhere else. And that means in the vacuum state, the Higgs doublet points in one particular direction of SU2 space and U1 space, and breaks that symmetry down to one U1 subgroup of SU2 cross U1, which is still conserved, and that is precisely electromagnetism mediated by the photon. That makes the W and the Z boson massive and leaves electromagnetism as the only long-range force in the standard model, but it also magically creates fermion masses. As it happens, the way that the representations are constructed here, all the fermions have a coupling to the Higgs. There's a left-handed fermion that couples to a right-handed fermion multiplied by the Higgs. For example, the quark doublet here has a coupling to one of the other anti-quarks here and the Higgs. And once the Higgs achieves its vacuum expectation value, this produces a mass term for the fermions. So for each fermion species, you have a separate mass term that is proportional to the vacuum expectation value of the Higgs, 200 GeV, multiplied by some unknown Yukawa matrix that you have to fit to the experimental data on the quark masses and mixing angles. The two quarks sitting in this doublet partner up with this singlet and this SU2 singlet, and one of the two components of this lepton doublet partners up with this singlet and forms the electron Dirac spinor. This still leaves one component of this doublet that doesn't have a partner. If you can tell that there's one extra state missing that was needed in order to make all fermions massive, and that is precisely the partner state of the neutrino. For neutrinos in the standard model, there's no right-handed partner to write down such a coupling, and as a result, the neutrinos remain massless even after electroweak symmetry breaking, because you just don't have the right degrees of freedom to make a massive Dirac spinor out of them. So one of the standard model predictions is that neutrinos are massless. For some other predictions, we have a closer look at the Lagrangian. One thing you realize is that it has more symmetries than the ones we imposed. We imposed Lorentz or Poincaré symmetry to conserve angular momentum, etc. And we imposed the gauge symmetries. But in addition, the Lagrangian has 4 U1 symmetries that come out accidentally, or at least some people think that it's accidental. For one of them, we simply need to rescale all quark fields by a common constant phase. This leaves the Lagrangian completely invariant, and since it's a phase, it corresponds to a U1 symmetry. According to Noether, each symmetry brings with it a conserved quantity, and the conserved quantity here is quark number or baryon number. So the number of baryons minus antibaryons will never change in processes mediated by the standard model. Similarly, we can rotate all electron and electron neutrino fields by a constant phase and still get the same Lagrangian. So there's another U1 symmetry with conserved electron number, and then you can do the same for muon number and tauer number. So the classical standard model Lagrangian has these 4 U1 symmetries that are a prediction of the standard model. We didn't put them in. The first one, baryon number conservation, forbids proton decay. It makes sure that the proton is infinitely long-lived, which is pretty good to make stable matter. And the other lepton symmetries here, they forbid, for example, a muon to decay into an electron and a photon. Less important than proton decay, but still something that, that we can test. All right, this was just at the classical level. 't Hooft has shown a long time ago that when you look at the quantum level, there are non-perturbative processes called instantons that break the total sum of these charges. So B plus L is violated at the non-perturbative level, and you can imagine processes like this with one flavor of each neutrino and then a bunch of quarks that form an electrically neutral object here. And you can imagine these as tunneling processes. And as tunneling processes, they are exponentially suppressed by the small SU2 gauge coupling constant, to the point where these are so small that we have never and will probably never observe these. Theoretically, though, B plus L is violated at the quantum level in the standard model Lagrangian. Even though these are exponentially suppressed now at low temperature, at high temperature, in the hot early universe, these processes, which we then call sphalerons, are very efficient. They are in thermal equilibrium with the rest of the standard model plasma, and they mediate B plus L violating interactions. This is something that we will talk about some more later, because that is a potentially useful ingredient to explain the baryon asymmetry of the universe. All right, so since B plus L is violated, even though it's difficult to observe, the actual global symmetry group of the standard model consists of these 3 U1 symmetries, B minus L, and then 2 flavor differences. The question is this standard model prediction a deep fact, or just an accident that we shouldn't think too hard about. For the sake of the argument here, I will assume that this is a deep fact that the standard model is telling us, and we should try to take this symmetry group as seriously as we can. That in particular means that we should try to promote it to a gauge symmetry, because we think that quantum gravity will violate all global symmetries. We can think about it as throwing charges into a black hole that then disappear and essentially violate any global symmetry. Only if a symmetry is connected to a massless gauge boson can the black hole carry that charge and lead to a conservation of that charge in the entire universe. So unfortunately, we can't just say that this is a gauge symmetry. You can't just declare it and think you'll be successful. It turns out to be mathematically inconsistent to just gauge this. You have to introduce extra leptons to do that. And you find that the quantum numbers of that extra lepton are such that it's a total singlet under the standard model gauge group. So it doesn't couple to any of the gluons, W bosons, or photons that we know. But it does need to carry electron, muon, and tauer number. So these are singlets under the gauge group, completely neutral or sterile, and they carry electron, muon, and tau number, so they are kind of neutrinos. That's why we call these things sterile neutrinos. They behave like left-handed neutrinos, but come as right-handed particles and are complete singlets under the gauge group. This increases the symmetry of the standard model, allowing us to promote the global symmetry to a gauge symmetry. This is partly the motivation to introduce 3 right-handed neutrinos to the particle content of the standard model. Another motivation or a neat side effect of this is that now each generation of fermions looks like this. It's just the previous thing plus this new singlet. This looks even worse because you have an extra piece in this highly reducible representation. But it turns out with this missing piece, the whole thing fits perfectly into the 16-dimensional representation of SO10. And SO10 contains the standard model gauge group as a subgroup. This could be a hint of why the fermion structure in the standard model is the way it is, why the standard model fermion representation takes this form, simply because, and also why the standard model gauge group looks the way it is, seemingly randomly a product of groups. You can imagine that the whole thing just used to be an SO10 and a 16-dimensional representation that was then broken down dynamically to what we see at low energies now. This is a nice motivation to introduce these right-handed neutrinos as well. So overall, sterile neutrinos increase the symmetry of our theory. What are the consequences? Well, once we add these right-handed neutrinos, since they are singlets, they don't couple to any gauge bosons. In fact, the only coupling that they do have is a coupling to the left-handed lepton doublet and the Higgs doublet. So you get a standard Yukawa term. And when you expand this out after electroweak symmetry breaking, you find that this is nothing but a neutrino mass term. This is exactly the same mechanism that it's effective for the charged fermions in the standard model, because the right-hand neutrino here has precisely the right quantum numbers to partner up with the left-handed neutrino and form a massive Dirac particle, just like all the other fermions. It's the most straightforward solution to get neutrino masses, and we have motivated it kind of backhandedly through increasing the symmetry of the model. All right, if we take the symmetry here seriously, these two terms would forbid any mixing angles in the neutrino sector. You'll basically find that this mass matrix is forced to be diagonal. This is very different from the quark sector, where the up and the down quark matrix need not be aligned, and as a result, you get a mixing in the quark sector that is parameterized by the Kabibo-Kobayashi-Mascava mixing matrix. Because of this, and with a bit of hindsight, we will not impose these two U1 symmetries on our Lagrangian. We will let them go and simply assume that B minus L is a good symmetry that still motivates the addition of the right-hand neutrinos. The same argument goes through whether you have these two U1s or not. So let's just drop them for now and just take B minus L as a good symmetry, as a motivation to get these right-hand neutrinos, which then have a non-diagonal mass matrix, and you get the CKM analog, the Pontecorvo-Maki-Nakagawa-Sakata mixing matrix in the lepton sector. At this point, from the theory side, we have no prediction for the neutrino masses or the mixing angles, but this is the qualitative prediction that you get from adding 3 right-handed neutrinos. Why are particle experimentalists excited about this? Because this is something we have observed in the form of neutrino oscillations. For a couple of decades now, we have done experiments with neutrinos and found that the electron, muon, and tau neutrino are not the mass eigenstates. They have masses and they mix, leading to neutrino oscillations. Let me give you a brief overview of how this works. You basically assume that the neutrino mass eigenstates are linear combinations of the flavor eigenstates with precisely this PMNS mixing matrix U, a 3x3 unitary mixing matrix that tells you how these two bases are related. Now, let's say you create a would-be tau neutrino in a decay like this. Tau goes to pi minus and a tau neutrino, but now we should really think about this as emitting a mass eigenstate J. And the amplitude for this goes with an entry of this U matrix that connects tau to J. This mass eigenstate now propagates as a plane wave, let's say, and eventually does something else that we use to detect the neutrino. For example, it creates a charged lepton of flavor alpha. And the amplitude for this will again be given by the entry in the mixing matrix here. Since we don't observe the mass eigenstates directly as they propagate, we have to sum over all possible mass eigenstates here. And if we assume that the masses of these neutrinos are not degenerate, they will travel with slightly different velocities as they make their way to the detection point here, allowing for different phases of the different mass eigenstates. This allows for interference between the different mass eigenstate contributions after the neutrinos have traveled a distance L. To get the probability to get flavor alpha from this tau event, you just multiply these 3 pieces, the phase factor due to propagation and the 2 production and detection probabilities from the mixing matrix, and you get the famous neutrino oscillation formula. It is sensitive not to neutrino masses, but to the difference of neutrino masses, because the relevant quantity here is how different the velocities of the mass eigenstates are. You can also see directly that you can kind of get rid of one of these exponential factors, and you only end up with mass square differences in the argument here. We have done this experiment with many, many different sources and detection materials over many distances and energies, and have confirmed this basic picture for neutrino oscillations, which allowed us to extract what this mixing angle U, mixing matrix U looks like. And the absolute values look something like this. Vastly different from the quark sector, but perfectly well described by this unitary 3x3 matrix. And we've also measured the 2 mass square differences that we have for 3 massive neutrinos. And we found that these are tiny. Because they are tiny, this interference happens on possibly macroscopic distances. You have a quantum interference effect over hundreds of kilometers due to the fact that the mass splittings are so small. Now, the mass splittings don't tell us anything about the absolute neutrino mass scale, but we have separate experiments like Katrin in Germany that looks at beta decay spectra and puts an upper bound on the absolute neutrino mass scale of 0.8 electron volt. So overall, neutrino masses are definitely tiny, much, much smaller than any other mass we know. And there's a huge experimental program to pin down the last remaining parameters, for example, the sign of this mass splitting and the absolute neutrino mass scale. But for now, this is good enough for us. Let's get back to the sterile neutrinos. Can we detect these right-handed sterile neutrinos that partner up with the left-handed ones to form these mass eigenstates? Unfortunately, no. They have no gauge interactions, which already makes it much more difficult to produce or detect them. And the only coupling they do have is this coupling to the Higgs that is proportional to the neutrino mass. Since neutrino masses are so small, that coupling is smaller than 10 to the minus 11. That is too small to produce or detect these right-handed neutrinos in any experiment that we can think of. Even in very sensitive quantities like lepton flavor violating decays, you wouldn't see any of these effects because they're all suppressed by neutrino masses. The only observable effect these sterile neutrinos have is in neutrino oscillations. Now you might say, this is just semantics. Why can't we just take these neutrino oscillations and say that they serve as proof that these right-handed neutrinos exist, and we're done with it? The problem is that there turn out to be more than one way to get neutrino masses. Once you look at Majorana neutrinos, there are ways to give masses to neutrinos without having right-handed neutrinos, and that still give the exact same neutrino oscillation formula. So neutrino oscillations tell us that neutrinos have mass, but not what kind of mass, and by extension, not what kind of new particle we need to introduce to make them massive. This is why we have to be careful to not confuse neutrino oscillations with the detection of right-handed neutrinos. They would be a simple solution to this, but not the only one. So we still have to hold off on declaring observation of right-handed sterile neutrinos. All right, not only are the couplings too small to make and detect these right-handed sterile neutrinos, now they're even so small that in the early universe, when temperatures were high enough that Higgses were zipping around, even then you didn't make a testable amount of right-handed neutrinos. It is that small. Now it sounds like I'm beating a dead horse here, but this is actually a potentially interesting consequence of these right-handed neutrinos. Because if they never thermalized with the rest of the standard model, even in the early universe, we can use them to explain the matter-antimatter asymmetry of the universe. If you look around you see that everything is made of matter and no antimatter. But in the standard Big Bang picture, you would assume that there's an equal amount of matter and antimatter initially that then annihilates away and only leaves over the excess of matter over antimatter, which then needs to be generated dynamically. This can happen through a process called Dirac leptogenesis. The idea doesn't work out of the box. You need to introduce extra particles that I will call X that couple to the right-handed neutrinos and also to other standard model particles. You can see a full list of possibilities here, but for now, let's just assume that it's a scalar with charge 1 that couples to electrons and neutrinos and decays into electrons and neutrinos, both left and right-handed. We assume this particle to be very heavy, but since it has electric charge, we know in the early universe it was in equilibrium with the rest of the standard model and was produced in large quantities. Once the temperature due to the expansion of the universe dropped below the mass of this new particle X, the abundance of X and X bar starts to become exponentially suppressed, the standard Boltzmann suppression, until you hit a small density that makes it difficult for X and X bar to find each other to annihilate. That is the point we call the freeze-out temperature, at which point X and X bar stop annihilating and the abundance of X is almost constant, frozen out, until X starts to decay away, which could be a good bit later, and would be out of equilibrium at that point. The equilibrium abundance is given by the dashed line here. When it decays, by construction, it will produce right-handed neutrinos. We build this thing so that it decays into these right-handed neutrinos and antineutrinos and gives you a potentially large number of these right-handed neutrinos. And in fact, since at the point where it decays, the standard model bath has cooled down potentially significantly, you are shooting these right-handed neutrinos out with a pretty high momentum relative to the standard model bath. Since it doesn't talk to the standard model bath, it keeps this higher temperature relative to the standard model particles. And that effectively looks as if you introduced a large amount of additional radiation to the universe. You have this separated bath of highly relativistic right-handed sterile neutrinos that are zipping around and would change the expansion rate of the universe. This is usually parameterized by the effective number of neutrinos, N effective. So if cosmologists can improve the measurement of N effective significantly, they might be able to see an effect due to these light sterile neutrinos. But that's not even the interesting aspect of this. The interesting part is that the decay of X is typically CP asymmetric. At loop level, you can show that X can have a asymmetric decay rate. That means if you have an equal amount of X and X bars decaying, in the end, you end up with more right-handed neutrinos than right-handed antineutrinos. So you have an excess or an asymmetry in the final number of right-handed neutrinos over antineutrinos. That is completely irrelevant because you can't see that, that bath anyway. But since B minus L is conserved the entire time, that asymmetry in the right-handed neutrino sector has to be matched by an asymmetry in B minus L. In this particular example, it's just an asymmetry in the left-handed neutrinos. Those two exactly cancel each other, but since the two baths don't talk to each other, they remain non-zero asymmetries. This is where it gets interesting, because in the standard model bath, you have these sphalerons that break B plus L and therefore see this lepton asymmetry that we have effectively generated in the standard model bath, and they will convert the lepton asymmetry to a baryon asymmetry. And then it's just a question of getting the right numbers to explain the baryon asymmetry that we've measured in our universe. Even though B minus L is never violated, we essentially smuggle part of the asymmetry past the sphalerons in this hidden bath made up of right-handed sterile neutrinos. And this only works because the neutrino masses are so small that the Yukawa couplings to the Higgs are small, so that the right-handed neutrinos are not thermalized. So it uses the fact that neutrino masses are small for something very exciting. Not going to go into detail here, but this is a plot that shows the kind of interaction strength of these X particles versus their mass and what kind of asymmetry you can get out of them. And take my word for it, it is a very efficient mechanism to get the observed baryon asymmetry. As long as the X masses are pretty massive, 10 to the 9 to 10 to the 15, let's say, you can easily generate the right abundance. In the dark red triangle here, you would get too large a contribution to N effective. So this region is already excluded because these X decays would produce too high energetic new Rs to be compatible with what we know about the radiation density in the early universe. But everywhere else, it's fine for now. In the light red shaded region, we can expect cosmological data to eventually be able to be sensitive to the contribution from these right-handed neutrinos. So this is the region that we can test in the near future with the CMB stage 4 experiments. Maybe they see something. If not, you can get the right baryon asymmetry in that region of parameter space. All right, so overall, adding sterile neutrinos to the standard model increases the symmetry and allows you to promote the global symmetry of the standard model to a gauge symmetry. It also completes the 16-dimensional representation of SO10 and allows you to think about the standard model as being embedded in a grand unified theory, a simple theory like SO10. The practical upshot is that you make massive Dirac neutrinos that can explain neutrino oscillations and solve one of the biggest problems the standard model has. In addition, you can also explain the matter-antimatter asymmetry. The downside is that you will never be able to see these new Rs directly in any experiment. All right, but there is more. As if this wasn't exciting enough, there's one extra thing you could think about. Namely, so far we've motivated the existence of these right-hand neutrinos by looking at the global standard model symmetry, U1 times U1 times U1. But neutrino oscillations already tell you that the last two U1s here are definitely broken in nature. Otherwise, you wouldn't have these non-zero mixing angles. But if 2 out of the 3 U1s are definitely broken, who tells you that the first one shouldn't be broken as well? Maybe B minus L is not a good symmetry of our universe. Maybe it is broken just like the other symmetries in the standard model. Let's play with that. If it's broken, and we still introduce our 3 right-hand neutrinos, we can write down one additional term in the Lagrangian. It's this one that manifestly breaks lepton number by 2 units. Otherwise, it wouldn't have shown up already in the previous case. So we interpret this as a Majorana mass term for the right-hand neutrinos. It means the right-hand neutrinos are their own antiparticles, an option that is really only available for neutrinos because they're the only neutral elementary particles that we know. So only they would even pose the question of whether they're their own antiparticles or not. So far, previously in the Dirac case, they were not their own antiparticles. Here, they turn out to be their own antiparticles. And this leads to drastically different phenomenology, in no small part because we're adding a bunch of new parameters to play with. So depending on what you do with this matrix, you can get a lot of different signatures out of it. Let's look at the mass generation first. In addition to this Majorana mass matrix, you also have the Dirac mass matrix from electric symmetry breaking that mixes the left and the right neutrinos into each other. So overall, you end up with a 6x6 block matrix for the 3 left-handed and 3 right-handed neutrinos that contains of the Dirac mass block and the Majorana mass block. And in general, you need to diagonalize this and find the eigenvalues and make sure this is consistent with neutrino oscillation data. In one very popular limit, you can do this almost analytically or at least systematically. If you assume that the Majorana mass is much, much bigger than the Dirac mass, you can expand the whole thing out in block diagonal form in powers of md over mm. And you find that the spectrum splits into 2 different pieces. You find that 3 of the neutrinos get a very large mass that comes from this mm mass matrix. And the 3 other neutrinos come with a small suppressed mass matrix that is given by this seesaw formula. This is suppressed by the heavy mass scale. So you can make it arbitrarily small just by increasing mm, by splitting the spectrum even further. This is the seesaw mechanism. That is very popular because it allows you to explain why neutrino masses are so small, not by putting in tiny Yukawa couplings of order 10 to the minus 11, but rather by having order 1 Yukawas potentially and just heavy right-handed neutrinos that suppress the active neutrino masses. There's also going to be a mixing between left and right-handed neutrinos that is given by md over mm. So naively, it is also very small because it's suppressed by the active neutrino masses and these heavy Majorana neutrinos. In terms of a bit of a picture, before we had these Dirac neutrinos, so left and right-handed neutrinos partnered up to form 3 massive Dirac neutrinos. When we have this Majorana mass matrix, very big, the 3 Dirac neutrinos split into 6 Majorana neutrinos, 3 of which are heavy and mostly the right-handed neutrinos. We will call them N from now on. And the other 3 are mostly the left-handed one, and these are the light neutrinos. These are the ones that actually oscillate in neutrino oscillation experiments. All right, why is this exciting? Because it gives us new things to look for. In particular, since now lepton number is broken by 2 units, you can look for lepton number violation. And one of the best ways we think we can look for this is through neutrinoless double beta decays. We have observed normal double beta decays, which are just 2 beta decays happening at the same time, emitting 2 neutrinos. But if neutrinos are their own antiparticles, you can connect the neutrino lines in the diagram here and let them be virtual particles. You no longer need to emit 2 neutrinos. You can make them stay inside and only emit 2 electrons. So this is manifestly neutrinoless. And it's a good signature to look for because you know exactly what the energies of these electrons are. They're sitting at the end of the typical double beta spectrum. This would be a clear evidence for Majorana neutrinos. If we found this lepton number violating decay, there would be no doubt that neutrinos are Majorana particles. And we have looked for this quite a bit with limits currently of order of 10 to the 26 years and a dedicated program to push this further in the hopes of eventually finding this decay, confirming that neutrinos are Majorana particles, and maybe even measuring important mass properties of the neutrinos. So far, we haven't. Let's get back to the sterile neutrinos, the heavy Majorana neutrinos, because they can do similar stuff. You could hope to detect them in many other ways. For example, we can go back to lepton flavor violation and check if these new heavy Majorana neutrinos can increase the rate compared to what you would have in the Dirac neutrino case, where all these rates are suppressed by neutrino masses and unobservably small. And indeed, you find that there's an additional contribution now from the Majorana neutrinos that looks like this, that is naively of order of neutrino mass squared and therefore highly suppressed. But since we're looking at matrices here, there is the possibility of having matrix cancellations in the neutrino mass matrix so that this product of matrices is small, even though Mn is pretty small and Md is pretty large. This is precisely the region that is easy to test for experimentalists. If you assume the naive seesaw scaling, basically treat this as if these weren't matrices, then it becomes very hard to see the right-handed neutrinos or the heavy Majorana neutrinos. Whereas if you assume that there's a matrix cancellation here, you can have large mixing angles between left and right-handed neutrinos, even though the massive neutrinos are fairly light. This is the region of parameter space that is easiest to test. It's a bit fine-tuned, but there are even ways to motivate this from extra symmetries. This is strictly speaking not in the spirit of the seesaw mechanism, because you would use matrix cancellations to suppress the mass rather than scales. But still, it's a viable region of parameters in the seesaw framework, so we don't distinguish much between this. So if you use these cancellations, you can make mu to E gamma or other lepton flavor violating rates observably large, offering the exciting possibility of potentially seeing lepton flavor violation mediated by something that is connected to neutrino masses. If they are sub-TeV, you can even hope to produce these heavy neutrinos directly. They will be produced with a amplitude suppressed by the mixing angle in any process that generates neutrinos. So for example, at the LHC, you could have an annihilation of quark-antiquark into a W that goes into an electron and a neutrino, and with some probability given by the mixing angle, you make one of these heavy Majorana neutrinos that then eventually decays through the same mixing angle, for example, into an electron and jets, nicely visible. This is the best hope of observing lepton number violation at colliders by having on-shell Majorana neutrinos that then decay in this way. Unfortunately, in this fine-tuned region where you make the mixing angle large and Mn small, you typically suppress these rates. There's a destructive interference between the different contributions that makes this a little bit less likely. So typically what dominates is the lepton flavor conserving mode where there's an E plus here. In any case, we can look for this in many different experiments. This is a plot of current constraints of the mixing angle of one of these right-handed neutrinos with the electron neutrino as a function of the heavy neutrino mass. Again, above TeV, you can't really make this on-shell in any experiment anymore, and you only have indirect constraints. But below TeV, there's actual collider constraints that probe some region of the parameter space. The green diagonal here shows the predicted seesaw relation. So this is naively the relationship between mixing angle and right-handed neutrino mass. And as you can see, we don't really probe that region. This is a difficult to access region. But with this fine-tuning I mentioned, you can actually live up here. So these limits probe viable parameter space. Let's look at future limits. In the future, Dune, Ship, Pioneer, they might be able to dip into this seesaw-motivated region shown here, but definitely will improve limits in this kind of fine-tuned region up there. All right, so experimentally, having heavy Majorana neutrinos offers many new ways to look for signals. There's additional motivation for these heavy Majorana neutrinos from cosmology, again, from the matter-antimatter asymmetry. And the idea far predates Dirac leptogenesis, but is very similar in spirit. You assume that these heavy Majorana neutrinos are very heavy. In that case, the mixing or the Yukawa coupling to the Higgs is pretty large, and you can produce them in large numbers in the early universe. Once the temperature drops below their mass, they freeze out, then they eventually decay out of equilibrium into a left-handed lepton doublet and the Higgs doublet. And in general, once you take loop effects into account, this will give you a CP asymmetric decay that generates, in the end, more leptons than anti-leptons, or the other way around. So you've created a lepton asymmetry in the decays of the heavy Majorana neutrinos. And from there on out, it's the same picture as the Dirac leptogenesis. Sphalerons that are in equilibrium in the standard model bath will take this lepton asymmetry and convert it into a baryon asymmetry, and you just need to find numbers to get the right measured amount of matter-antimatter asymmetry. It turns out it's easiest if the masses are between 10 to the 10 and 10 to the 15, as seen here. But even below, you can make it work by having some resonant enhancements in some of these diagrams. The interesting part is that this mass scale where baryogenesis works matches up very well with the mass scale that you naively expected from the seesaw mechanism. To get the electron volt active neutrinos, you expected these heavy neutrinos to be of order 10 to the 13 GeV. So this nicely confirms kind of the seesaw idea in a nice way. All right, lastly, let me tell you why astrophysicists are excited about sterile neutrinos. They are, after all, massive neutral particles, so they could form dark matter. Now, they are unstable because due to the mixing, they will decay into 3 neutrinos or a neutrino and a photon. But as long as the decay is very rare, as long as this new particle lives for at least as long as the age of the universe, it's still good dark matter. If you want to make that happen, if you want to increase the lifetime, you need to make the mass of this particle as light as possible and have a small mixing angle. There's a bound on how low you can make the dark matter mass if it's a fermion, just from the Pauli principle, which tells you you can put only so many fermions into a volume the size of a galaxy, and that typically comes out to be keV. That's why we usually call this keV sterile neutrino dark matter, because it needs to be at least keV to be good dark matter. And then you need to fix the mixing angle to suppress this decay, because this decay is a very nice signature. It's dark matter decaying into a monoenergetic photon. And with a keV mass range, this is an X-ray photon. This is something people have looked for and not found, putting strong constraints on the mixing angle. So strong indeed that we know that this sterile neutrino doesn't contribute to active neutrino masses. It would need a much larger mixing angle for that. So implicitly, this predicts that the lightest active neutrino is massless. You can get the right abundance of this dark matter by playing with the mixing angle. And at this point, since the minimal scenario is already ruled out, you also need to create a very large lepton asymmetry that resonantly enhances the production of the dark matter. This goes by the name of the Shih-Fuller mechanism. That is basically everything above this BBN line. Here, you get the right amount of dark matter and evade X-ray constraints. So this is a viable scenario for sterile neutrino keV dark matter. So we can use 3 massive Majorana neutrinos to get neutrino masses, the baryon asymmetry, or dark matter. In a very ambitious model called the new MSM, Asaka, Blanchard, and Shaposhnikov showed that you can actually do all 3 at the same time. You can use 2 of the massive neutrinos to get the right neutrino mass splittings in neutrino oscillations and to get the right matter asymmetry, and you use 1 as a dark matter candidate. This is a highly testable scenario that solves the 3 biggest issues of the standard model in one fairly efficient swoop. And with that, let me conclude. Sterile neutrinos increase the symmetry when added to the standard model. They also generate massive neutrinos, Dirac or Majorana, and therefore explain neutrino oscillations. Dirac or Majorana, you can explain the matter-antimatter asymmetry as well. And even though it is difficult to observe these sterile neutrinos directly, there's hope to see them in neutrinos double beta decay, lepton flavor violation, or collider signatures. And last but not least, they could also form dark matter.